All right. Hi, everyone. Good morning. Welcome back. We continue our descent into trigonometry. And we saw in the last video that trig can be used to create a new area formula for triangles. And what I want to show you today, or in this video, is how we can start using trigonometry to find missing sides and missing angles of non-right triangles. This is a big step for you all because up until this point, trigonometry has always been right triangles. And what we're going to see today is actually we can extend it. And there are a couple formulas that work with non-right triangles that turn out to be really, really useful. So to jump into this, I've got this diagram here. Everything is labeled generally. So notice I have capital A, capital B, capital C on the vertices, and the sides are labeled lowercase a, b, and c. Also notice the placement of these letters is deliberate. Capital A angle is across from lowercase a side. Capital B angle is across from lowercase b, same with c and little c. I've got this line dropped down here. This is supposed to be the height of the triangle. I forgot to draw in the right angle there, and I've labeled that part x. We're going to derive a formula using this picture because this picture could really represent any triangle in the universe. We can take any triangle in the universe and label these points and sides accordingly, and we could drop a height down in the interior, right? We could do that with any triangle. So any relationship I find in this picture must be true for all triangles. Part A says, write a trig equation that shows a relationship between x, a, lowercase a, and angle b. Well, we have a right triangle right there. So the relationship there would be the sine of angle b is equal to the opposite over the hypotenuse. Or in other words, the sine of angle b would be equal to x over a. Part B says, write a trig equation that shows a relationship between x, lowercase b, and angle A. Well, very similarly, x, b, and a are part of this right triangle over here, so I could say that the sine of angle A is equal to opposite over hypotenuse, or in other words, the sine of angle A is equal to x over lowercase b. These two statements are true, right, based on this picture. Part C says to solve both equations for x. Well, if I was to do that here, I would multiply both sides by a, and I would get a times the sine of b. And using the same technique here, I would multiply both sides by b, and I would get b times the sine of a is equal to x. Well, if x is equal to a sine b and x is also equal to b sine a, then aren't those two things equal to each other? Why, yes, they are. And that's what I'm getting at. So I did that part there. That's what I'm getting at here in part D. All right, so if a times the sine of b is equal to x, and b times the sine of a is equal to x, then they must be equal to each other. And it's not hard to see that with a little algebra, I could divide both sides by a and divide both sides by b, and I would get that the sine of b over lowercase b is equal to the sine of angle A over lowercase a. Now that doesn't seem like much, but that's pretty significant. Think about this. This is telling us that the ratio between the sine of an angle and its over its opposite side, that's equal to the ratio of the sine of another angle over its opposite side. This says, what do you think is probably true about sine c over c? If you're thinking, well, these must also be equal to sine of angle c across from its opposite side, lowercase c, then you are correct. This relationship is true whether the triangle is a right triangle or not. This relationship is a way we can use trig in non-right triangles. And this is called the law of sines. And so I want to show you how this works. It's pretty easy, actually. So if you're following along on your own copy of these notes, you want to jump to the back side where I have the law of sines. It's extremely powerful because it allows us to use trig to solve for angles and lengths of any triangle, not just right triangles. The law of sines states that for any triangle, A, B, C, and we'd have opposite sides, lowercase a, lowercase b, and lowercase c. It is always true that the sine of angle A over little a is equal to the sine of angle B over little b, which is also equal to the sine of angle C over little c. So how does this work in an actual problem? Well, let's say we had a triangle like this. This is a non-right triangle. It's asking us to solve for x, this missing side. We're going to use the law of sines. What you want to do with the law of sines is look for angles that we know across from sides that we know. In this case, I have this angle and this side are across from one another, and we have values for both. So using the law of sines, I could say that the sine of 63 degrees over its opposite side, 12, is equal to the sine of this angle over its opposite side, x. And here is now an equation that we can use to solve for x. I don't know about you guys, but whenever I solve these types of equations, this is called a proportion, when you have like one fraction equaling another fraction. I always like to use what's called the cross multiply method. And the cross multiply method, you may recall, says that I can set the cross products equal to each other. In other words, I can say that 12 times the sine of 92 is equal to x times the sine of 63. And now all I have to do to solve for x is isolate that variable. And so remember, sine of 63 is just a number. So we're going to divide both sides by the sine of 63. And we get 12 times the sine of 92 over the sine of 63 is equal to x. And there is our solution. At this point, we're going to have to grab the old calculator and type this in. So we'll do 12 times the sine of 92 divided by the sine of 63. And we get 13.46. The law of sines. It's really, really nice, and it's fast, actually. So here we had two angles and a side, and we solved for a missing side. Wouldn't it also make sense that it's possible to have two sides, one angle, and then solve for a missing angle? And the answer is yes, we can. So let me show you an example of this. The algebra is going to be slightly different here, but the setup is the same. We're going to use the law of sines. So the sine of 68 over 24 is equal to the sine of this angle, which is x, over 23. The setup is the same, but notice the difference now in this problem. In this one, x was a side length, right? And so x was in the denominator there. That was pretty easy to solve for. We just did the cross multiplying, isolated the x, and we were done. Here, the x is inside this sine function, okay? So the first thing we're going to want to do is isolate this term. So we're going to start this the same way. We'll cross multiply. So 24 times the sine of x is equal to 23 times the sine of 68. And now to isolate the sine of x, we're going to divide both sides by 24. And so I get this. Sine of x is equal to 23 times the sine of 68 over 24. Okay, so here we have a case where we know the ratio here, but we don't know this angle. Remember, when that happens, you might recall when we reviewed trig last week, we have to use inverse trig. So this is a case where on my calculator, I'm going to use the inverse sine button, and I'm going to input this amount. I'm going to input 23 times the sine of 68 over 24, and it will output for me the angle x. And so at this point, I'm going to have to grab my calculator again. We'll use that inverse sine button and then type all this stuff in. So 23 times the sine of 68 divided by 24, and we get 62.69 degrees. Okay, and there it is. The law of sines. This is a very famous, very useful trig formula that we can now use to find missing sides and missing angles of non-right triangles. So on your assignment for this week, you're going to see some practice problems that have you finding triangle area. You can refer to my previous video to review that. And you'll have several problems where you need to find missing sides or angles using the law of sines. All right. Hope you guys have a great week, and we'll see you next time. Take care.